Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to be looking at ground signal ground designs because we just recently received one of these types of designs in the 1-minute design review series. Now in these designs, they flip the traditional 4-layer architecture inside out. Normally you have routing on the outer layers and then you have 2 internal planes. And if you have 2 internal ground planes, you can of course flip that so that the planes are on the outside and then your signal routing is on the internal layers. What we're gonna do in this video is we're gonna take a look at the 1-minute design review submission that brought up this whole topic for this video. Then we're gonna look at 2 other designs that show how to do the internal signal routing correctly, particularly in the case where you have digital signals on the interior of the board. Let's go ahead and hop into Altium and get started. In today's discussion of ground signal ground stackups, we are going to be looking at a 1-minute design review submission from Konstantinos Kyriazis. And this submission was on a 4-layer board. It is more of a power board because it is for a door lift system, but it illustrates a few really good points that you need to follow when you're working on a ground signal ground stackup. We're also going to take a look at a couple of other designs. One of them was a different 1-minute design review submission, and these are on 6 layers. However, in these designs, we have 2 internal signal layers, just like we have with a ground signal ground stackup. And those types of designs very nicely show how to handle routing on the internal signal layers when you have a lot of signals, including a lot of digital signals. So here we have on screen the design from Konstantinos, and as you can see from the layer list down here along the bottom of the PCB editor window, this is a 4-layer PCB. When we scan through here, we can see what the internal layers on the bottom layer look like. And those of you with a good eye will probably notice a few things that need to be changed immediately in this design. And they're not major, hugely consequential things. One of the big ones is, of course, the fact that most of these components were pulled from the generic Altium library, and they don't have actual manufacturer part numbers attached to them. Now, they do come in actual packages, so that is helpful for constructing a PCB layout with actual component models. But of course, if you were ever going to build this board, you want to make sure that you use manufacturer components, not generic components. Just a few of the big things that we see here. We don't see any stitching vias that are clearly linking the top, internal, and bottom ground pores. We also see that we have the polygon running right up to the board edge. We don't have any clearance here, so we would need to add in a board outline clearance rule to automatically pull back this copper and leave some margin. We can see here on some of these symbols, it looks like we have some pretty thin silkscreen lines, and a manufacturer might email you and recommend that you thicken those up a little bit, so that way they will be printable and legible when you get the board manufactured. One thing that's interesting about this footprint on U1 is take a look at where these pin markers are located. Here you can see, if we just zoom in, that pin 1 is right here, but if we just isolate the top overlay layer, you'll see here that we don't have a pin 1 indicator. Instead, what we have is a pin 10 indicator. This is the first time I've ever seen this. And then we have a pin 20 indicator. And then if we just keep going around the footprint here, you can see we have a pin 30 indicator and then a pin 40 indicator. I've never seen anything like this in any integrated circuit footprint. So if anyone has ever seen that type of pin indication in an integrated circuit footprint, make sure to hop into the comments and let me know. Next, if I just zoom out here and grab the top solder layer, you can see here that a lot of the pads here, especially on U1, have no mask expansion. We want to allow for at least a little bit of mask expansion to allow for misregistration, but you can see here on this integrated circuit that we have a mask expansion of 0. Now, if I put this into 3D, you can see that there is mask expansion applied elsewhere, and you can see that the mask has been totally pulled off these vias. It's been applied somewhere else. You should make sure to go through and select those pads and then also apply the mask expansion there. And the last thing I want to bring up before we dive into the internal layer routing is to just look at the silk screen. You can see here that we do have silk screen falling on open solder mask. You can also see here on this header that we have silk screen falling directly onto exposed copper. So those things also need to be corrected in this design as part of the outer layer cleanup process. Now, if we keep looking through this board on the surface layer, there are some other things that I'm sure we could find. That's all well and good. I'll leave that up to the viewers. But what I want to focus on is the structure of this PCB stack up and how the routing is done and what lessons we can learn for ground signal ground stack up design. To get started, let's take a look at the layer stack manager for this board. So here we are inside the layer stack manager, and this is a ground signal ground stack up. And those of you that are familiar with Altium Designer will know that these layer thicknesses and copper weights all come from default values that appear when you do a right-click and insert layer above operation inside the layer stack manager. Now, normally we would want to start with a 1/2 ounce copper on the internal layer. We would want to do this on both of these internal layers. And the reason you want to do that is because the surface layers are going to get plated up to a full ounce of copper by starting from a 1/2 ounce of copper. So you would need to start from a 1/2 ounce in order to make that happen. Next, we would want to have our total thickness be one of the standard thickness values, either 1 millimeter or 1.57 millimeters. If we start with the outer layer dielectric for a ground signal ground stack up, well, remember, we're just basically taking the traditional signal, ground signal stack up and inverting it. So when we invert it, we would also use a thinner dielectric thickness value for those outer layer dielectrics. So we would want to use a value that could be, for example, let's say 6 mil. And if we use a 6 mil dielectric thickness here, we would then make up the rest of that thickness here in the internal core layer. And so we might set this to, for example, 45 mil. That gets us to a total thickness of 62 mil or 1.57 millimeters. Now, if you're inside the layer stack manager in Altium and you want to do a ground signal ground stack up, you'll notice here that you cannot select a plane option for the top layer. And that's actually intentional. That's because you have to put the components on the outer layers and you can't put components in a plane layer. So it forces you to use a signal definition for the outer layer. And then you'll have to do what you see here inside of this PCB layout, which is to use a polygon pour to define the ground net on the surface layers. So keep that in mind if you're trying to define any plane layers. You won't be able to define any plane layers in this stack up. You have to define the outer layers as signal layers. And then of course, these two inner layers, you're going to be routing there. So you also have to define these as signal layers. Now, one question that I think naturally comes up in this stack up is, can we do any sort of high-speed routing in this stack up? And can we do controlled impedance in this stack up? Well, the answer is yes, of course we can. We can definitely calculate a trace impedance from this stack up, and all we need to do is just go over here to the impedance tab, add an impedance profile, and then define which layers we're going to have controlled impedance on, and then what are the reference layers for those signals. So let's go ahead and define our two internal layers in this example as our routing layers. So here we have single-ended 50 ohm signals that we're going to be routing on an internal layer with these dielectric constant values. Now you can see here in this design that when we've defined the top layer and the third layer as our reference layers with the 6 mil outer dielectric on a 62 mil thick stack up, that we have an 8 mil wide trace defining our 50 ohm impedance. Now this is really important because in this calculation, it assumes that you are going to have grounded copper pour here on layer 3. Now, you don't have to have grounded copper pour on layer 3. You could have your copper pour on layer 4, and if that's the case, you would then want to pull down this bottom reference dropdown and select layer 4 right here for your other reference layer. You'll see that it then goes through and recalculates, and it basically comes out to the same value. In the previous case, with a reference on layer 3, you can see here that it's at 7.945 mils width for 50 ohm impedance. If we just set that to layer 4, you can see that it's 8.023 mils for 50 ohm impedance, basically the same value. So this should illustrate how important this top plane layer is for any of these signals that are being routed in this board. This top plane layer is going to be the main factor that determines the impedance for any of these signals that are being routed on these internal layers. Now that'll come in handy when we start talking about things like crosstalk, filling in the empty space with power, or any of those types of issues. Which of these layers is going to be prepreg and which of these layers is going to be a core? Well, by default, it has set the outer layer dielectrics as prepreg, but you could set these as a core layer. And that means in the internal layers, you would then have to build up a stack of prepregs to your target thickness and then use those to bond the core layers together into your final stack up. However, in most standard stack-ups that a PCB manufacturer will give you, that is actually not the approach that is taken. Normally, the outer layers are going to be the prepreg layer, and then you're going to have a thick inner core layer with your starting copper thickness laminated around that core. So you can see here we would have a stack-up that starts with this internal core layer, starting with 1/2 ounce copper. We then use the prepreg to bond the outer copper layers onto that, and then once we do our through-hole drilling, that's what's going to allow us to plate up that outer copper layer thickness up to this 1 ounce final value. So that's basically how we design this type of stack up. We don't have to use these dielectric values. We can use whatever materials are available from our manufacturer. They could have a mix of different dielectric constants. As long as we set them up in this type of configuration, this board is going to be manufacturable. Of course, make sure to start by looking at your manufacturer's standard stack up, because that is going to be a low cost option, and it's usually a pretty good place to start for a ground signal, signal ground type of stack up. Next thing I want to do is take a look at the inner layers and the outer layers and see how we can do the routing in this type of design. So here I want to focus just for a moment on one layer at a time. Let's take a look at the top layer. We actually do have a little bit of routing in this top layer, even though it is, by virtue of being a ground signal, signal ground stack up, it is supposed to be a completely uniform ground layer. Now, of course, we have to put the components somewhere, so you're going to have some cutouts in that ground region for all of your component pads so that you can solder your parts onto this circuit board. And that's exactly what you see here. But you can have a little bit of routing on this outer layer and still have it function effectively as a ground signal, signal ground stack up. So take a look here at the microcontroller right here down along the bottom edge of the board. You can actually see here that we have an unrouted net between these two pads. Now we could take a trace off, drop down here to an inner layer, and then access the power rail, but you can actually see here just by highlighting that the power rail for this net is located right here. So we could take a trace and, for example, just route right over here just like this. We would of course want to adjust the trace width, let's say down to, we'll go down to 15 mil, and then we would just end right here on this pad. We're going to adjust this just a little bit for acid traps, and then do a quick re-pour, and then this is what that trace is going to look like. So this type of thing is perfectly appropriate on a ground signal, signal ground stack up, as long as you don't interrupt the routing path for any signals on the internal layer. If we take a look at the bottom layer, you can see that we don't have really any routing except for one of these long lines on the bottom layer, but we could do the exact same thing. If we wanted to, we could also do a little bit of routing in this bottom layer between components. As long as we're not routing over those splits in the outer layer ground planes, then we're going to be fine. We're going to be able to maintain signal integrity, and we're going to have low susceptibility to external EMI. So now let's take a look at the internal layer routing. So here what I want to do is I want to just go ahead and turn off some of these component layers. We'll turn off the mechanical layers, and then we'll just focus on one or two of these layers at a time. So you can see here in this example, the routing is pretty good. If we just take a look at layer 2, remember layer 2 is referenced to layer 1, and you can see that a lot of these lines, for the most part, route over completely uniform ground on the outer layer, except on a few parts. Now, those areas where the traces don't route over completely uniform ground, what you can see that Konstantinos did is he put ground pour here on the inner layer. And that ground pour is supposed to provide a ground reference in these regions where the signals are being routed on this internal layer. Now, if you are going to put copper pour on an internal layer, you can do that. And if they are impedance controlled lines, you then have to use a single-ended coplanar impedance profile, not just the single-ended profile. So when you use a single-ended coplanar profile, you then have to apply a clearance limit on these lines. And by default, it is a 5 mil clearance between the line and the coplanar ground. Of course, you can make that clearance larger. You can make that a 10 mil clearance if you want. And you'll notice here, if we start to make that to a larger clearance, that's going to increase the width of that trace required for 50 ohms. Now we can see similar areas just like this if we look at layer 3 and layer 4 together, and then we turn off layer 1 and layer 2. There's just a couple of spots where some of these traces route over splits in the ground plane, but we do have the coplanar ground close enough that we are maintaining some type of ground reference right here in these regions. What we don't have a lot of in this design is ground stitching in these regions where we need to maintain consistent reference everywhere across this routing path. So what I would recommend doing in this design is if this line was carrying a digital signal, what I would do is maybe put a via right here in this region or right here in this region in order to ensure that the ground right here and right here are linked together and you can maintain a consistent return path across this split. Now, the preferable thing to do is, of course, eliminate the split altogether. And there are some ways to do that, which we'll see in just a moment. If you can't eliminate the split and you have to route over it, put a ground via here, put one here, do the same thing over here around these splits, and that's going to allow you to maintain a complete return path across both layers as you go through and do this routing. Now, let's take a look at layer 2 and layer 3 together and see what we can learn about these layers. Now, it's a little difficult to see both of these layers together because of the polygon pore, and it's basically opaque in this view. But what we can do is we can just go ahead and dim out the polygon pore significantly so that now we can see the routing together on both layers. Now, this is a pretty good way to do the routing on this type of board. What you can see here is that we have a lot of the traces running vertical in this region. We have some of these purple traces running vertical, and then it looks like we tried to run the orange traces horizontally. Now you can see here where there is one region where these purple traces, or this purple trace, is basically routing right alongside this other trace on layer 2. Now this purple line and this orange line being routed together in parallel like this creates what's called broadside coupling. And that's because you have the wide portions of the traces almost overlapping each other, and that creates higher capacitance between them than if you were to route them side by side on the same layer. Now, broadside coupling has the potential to create a lot of crosstalk compared to two traces on the same layer, or compared to coplanar coupling. So here, because we have a larger distance between the two signal lines, in this case we have 45 mil for a 62 mil thick stack up, that's going to help reduce the broadside coupling strength. And so we would expect that there would be lower crosstalk between those lines if they were carrying digital signals. Now, in this specific example, this is actually two different DC lines. Here you can see that this is plus 1 volt and this is plus 2 volts. So in this specific case on this board, we're going to be just fine on this because we're just carrying DC power. But on a different type of board where we might have a lot of digital signals routing on these two internal layers in a ground signal ground arrangement, that does create a risk of crosstalk. So to overcome that, we do what's called orthogonal routing. And orthogonal routing has somewhat been implemented in this design. But what I have are two other examples that show how to do orthogonal routing the right way. And the reason we do that orthogonal routing is to minimize the overlap between those traces and minimize the broadside coupling, and that minimizes the risk of crosstalk. First, let's take a look at one of our other 1-minute design review submissions for an RFID reader. Now, this design that you see here on screen is a 6-layer design, but if I turn off the top layer and the bottom layer and I just isolate the layers, you can see pretty quickly that this is a ground signal ground stack up. And we can then take a look at what the routing is just by looking at layer 3 and layer 4. So here you can see that we have very clearly implemented orthogonal routing between layer 3 and layer 4. Just go ahead and turn off the component layers, the mechanical layers, and the other layers. And then if we take the view configuration and turn off the polygons, you can see here that we have some very good orthogonal routing on these internal layers. So this is a good example of what orthogonal routing should look like. And it doesn't matter if you're doing this on a 6-layer board or on a 4-layer board with a ground signal ground arrangement. You can see very clearly how this should be done. There's very minimal overlap between any of these lines. You have one layer, lines routing horizontal. The next layer, the lines are routing vertical. Let's take a look at another example that very nicely shows this. So here, if I just go ahead and turn off these component layers, and then also turn off the outer layers, you can see here that we also have some very good orthogonal routing. So I'm going to go ahead and turn off the plane layers and zoom in, and you can again see exactly what this is supposed to look like. So we can do this again on a 6-layer board, or we can do it on a 4-layer board and essentially get the same effect. We have very minimal overlap between the traces running horizontally and the traces running vertically. And you can see here that we can still make these 45-degree angles just to space things out if we need to, or if we need to move over to another lane in this routing path on layer 3 or layer 4, we still have room to do that. And even doing that, if we just have any lines that end up like this, where they might be close together, all we have to do is just take one of these and move it out just a little bit. And that's going to help reduce reduce that broadside coupling between those traces. Now, so far, we have discussed this type of stack up just as a traditional build, where it just has a through-hole via. But of course, we could do a more exotic build like a sublamination build. So for example, we could have blind vias on the outer layer, and if we just click this and mirror it, we would then see what that looks like. We would have blind vias going from layer 1 to 2, and then from layer 3 to 4. Now, if these are mechanically drilled blind vias, of course, we would have to leave them separated around this core layer, and we would need to actually switch these. This would have to be core on the outside, and then we would have to have a prepreg stack on the inside in order to bond these two sublaminations together. So that's one way to do this. Now, we don't have to have only blind vias on the outer layer. We could, of course, move that blind via to an inner layer, and then we'd have a buried via. So that would basically look like this. And then we would also have to switch back. So we would need to have the core on the inner layer, and then we would build that sublamination first, and then we would bond these prepregs on the outside of that sublamination. We would also have an additional plating process, and so that would require us to build up the inner layer up to about an ounce if we're targeting IPC class 2, due to that plating process that's required to form this buried via. You could also do HDI with this type of design, where you basically just have one outer layer and then you have an internal core layer. But of course, that's going to put some restrictions on the thickness of that outer layer if you're then going to place microvias between layer 1 and 2, and then between layer 3 and 4. Now, those are a bit more exotic use cases, and I've never seen one done in practice. Normally, this is just a traditional build as we've been discussing here. But this case where you have the buried via on the inner layer, we did actually discuss that in another video, and you can find a link to that video in the description. Thanks everyone for watching this video, and thank you everyone for sending in your great design review submissions. And if you send in a good one, it just might end up in one of these deep dive videos. Make sure to hit the like button, hit the subscribe button, leave your comments and questions in the comments section, and last but not least, don't forget to call your fabricator folks. We'll see you next time.